So now we're going to look at a new example of Java streams and parallel streams, and we're going to see ways in which you have to be thoughtful about the type of collections you use based on the types of streams you create. And we'll see in particular that if you have collections that are based on implementations that are either inefficient to split or which split unevenly or both, when you try to use parallel streams, you'll get not very good performance. In contrast, if you have collections where the stream elements can be split up, the collections can be split evenly and can be split efficiently, then you get a much better performance when you use parallel streams. And the way we're going to do this is we're going to show the use of parallel and sequential splitterators on linked lists and array lists. And you'll also get a sense of understanding about how you combine the results together with sequential and parallel streams. So this particular example is kind of fun. I'm always a fan of anything involving William Shakespeare. So here we're going to have the complete works of Shakespeare, which is a large text source, as you'll see. And we're going to go ahead and run a bunch of tests. So we're going to start out by warming everything up. We're going to warm up the fork join pool so we get representative results because everything will be created. The threads will be up and running. Then we're going to run some splitterator tests. We're going to run some joining tests. And then we're going to run some collector tests. So let's go ahead and take a look at this. Let's start off by running the splitterator tests. And these tests are going to demonstrate the performance differences between using ArrayList and linked list splitterators. The way we're going to do this is we're going to create lists of 4 different sizes, 1,000, 10,000, 100,000, and up to 1,000,000. We're going to run out of elements in Shakespeare before that point, but it'll be around 800-some thousand input elements. And what we're going to do is for each of these value ranges, we're going to go ahead and get the input. And in this particular case, we're going to take the input, which is the complete works of Shakespeare, and we're going to split up the complete works of Shakespeare into words by ignoring all the white space. And we're going to see how many words there are in the complete work of Shakespeare. So that's our input. We get back a list of character sequences, which is the complete works of Shakespeare up to some limit. And you can see that we can designate the limit, which will either be 1,000, 10,000, 100,000, or all the words in Shakespeare, which again are like 833,000 or something. Then what we do is we take that list, which is an array list, and we also create a linked list. So now we're going to have an array list version of the complete works of Shakespeare and a linked list version of the complete works of Shakespeare. And then we're going to go ahead and do some timing tests. We're going to go ahead and time the amount of time to do some manipulations to the array list in parallel. And then we're also going to see how long it takes to do the same types of manipulations on the linked list. And of course, what we'd expect to see, as you might think, is that the parallel streams approach will work much better on the array list because it splits evenly and efficiently, whereas for linked list, it doesn't. Okay, so let's go ahead and run those tests. For the time being, let's comment out the join tests and the collector tests. And let's go ahead and run the tests. And so it's up and running. And you can see what it's doing is it's going through each of these iterations for the different sizes of the input. And so let's go ahead and take a look and see what we get. So for just 1,000 words, this is the first 1,000 or so words in the complete works of Shakespeare, the performance for splitting things up using parallel streams for linked lists and array lists, it's about the same. When we get to 10,000 words, you can see that array list is pulling ahead. It's taking less time because it's working in parallel better. When we get to 100,000 words, you can see that array list is definitely getting faster. And then when we get up to the complete works of Shakespeare words, which is 883,311, you can see that ArrayList is way, way faster at that point. It's basically going essentially at a linear speed up with the number of cores, because I have four cores, whereas the linked list version is much less efficient. So let's go ahead and take a look at the source code to kind of see why we're getting this behavior. So here's the actual test code that we're running. This is called time parallel stream uppercase. And what it does is it goes ahead and uses my little timing mechanism, and it goes for the number of iterations that we're going to be doing, which is going to be, again, basically, whatever we're setting this to be at any given point in time. And we're going to go ahead and create a parallel stream for all the words. And then we're going to go ahead and uppercase each work of Shakespeare's word. Every word in Shakespeare gets uppercased just to do something interesting with it, or not so interesting, but just to do some manipulation to it. And then we collect the results to a list. So this is going to go on for some number of iterations. We're going to do this just to make it interesting. And that's set to 10 by default. So we're going to go ahead and do these computations, stick the things at the end of this list that we're creating, and time how long that takes to run. And this is where the magic happens. Dot parallel stream, if you go look at dot parallel stream, which is here, whoops. What we're going to see here is, let's see if we can find it. So parallel stream, as you can see here, is going to call the splitterator for the collection. And the splitterator for the collection, of course, will then call either the splitterator for ArrayList or the splitterator for LinkedList. And if we were to take a look at splitterators for ArrayList or the splitterators for LinkedList, what you would see is that they work very differently. So the splitterator for LinkedList is inefficient and doesn't split evenly, whereas the splitterator for ArrayList splits evenly and efficiently. So that's why we get the big speed up there. Okay, so first point here is if you have collections and you want to use them in parallel streams, make sure the collections split evenly and efficiently. Now that we've shown that, let's go ahead and talk about the other side of the coin, which is joining and collecting. So now we're going to take a look at another example. This is called joining tests. And this is going to demonstrate the differences between concurrent and non-concurrent techniques for joining results in a stream. So what we're going to do here, as you can see, is this time we're going to stick with our array list because we already know that's the way to go. And once again, we're going to run these tests a number of times on different amounts of input, 1,000 words, 10,000 words, 100,000 words, and 883,000 words, basically. So we get the words, we start the joining tests, and you can see here that one time we're going to run this with parallel turned to false, so it's not going to be doing it in parallel. Another time we're going to run it with parallel set to true. So let's go ahead and run the tests, and we'll see what the results are, and then we'll come and take a look and see what the results mean and how they are implemented. So you can see here for the test for about 1,000 words, whether you're doing it in parallel or sequential, doesn't really matter. The input is small. When we do for 10,000 words, you can see that actually the sequential joining is a little faster, and that's due to the overhead of parallel computing, which we'll see in a second. When we get to 100,000 words, now parallel processing is starting to pay off. And then finally, when we get up to all the words in Shakespeare, the parallel joining is definitely way faster. And this is a classic example of the N times Q rule. So if you ever watch any videos by Brian Getz, who's one of the architects for Java, he has some really good videos on Java concurrency and parallelism. And he always makes the case that if you want to use parallel streams, make sure that N times Q is a relatively large number, where N is the number of input elements, and Q is the amount of time spent processing each element. So here, as we'll see, the larger the number of elements, the more the payoff from parallel processing. And in fact, as you see here, when we have a small number of elements, parallel processing can actually be worse because you spend more time doing parallelism setup and teardown than you actually do any work. So let's go ahead and take a look at the code. What we're going to do here is we're going to go ahead and use a string builder to keep our results, and we're just going to join things together. I probably could have used a string buffer here as well. I think they're roughly the same for the purposes that I'm using them here. As you can see here, what we're going to do is we're going to go through and take our lists of Shakespeare words, and we're going to convert them into a stream. And then if we're running with a parallel flag set, we're going to convert them into a parallel stream. And then what we're going to do is we're going to go ahead and collect them using the joining mechanism of collector. So collect has this joining collector, and the joining collector is this one here, and it basically joins things together. It essentially concatenates them together. And so this is really testing how fast can we join things together using sequential streams and parallel streams. And with, as you can see, when we run with parallel streams, we're doing things by splitting up the input first into chunks that are run in parallel, and then we go ahead and join them back. Now, in this particular case, we're not really doing anything else but joining things together in parallel. So you're able to get a speed up if you join things in parallel when n is large. You'll note here that Q is very low because we're not really doing any work here other than joining. So that's the second example, and the point of this example is just to show that as n gets bigger, the payoffs of concurrency go up. And the last test we're going to do is something called run collector tests, and this is going to demonstrate the differences in performance between concurrent and non-concurrent collectors. And this is going to be a really interesting experiment. You see, we're going to have a bunch of different variants here. As before, we're going to have the different sizes of inputs from Shakespeare, 1,000, 10,000, 100,000, and 883,000. And what we're going to do is we're going to try all the different combinations. We're going to both use a non-concurrent collector, both in parallel and sequential. And then we're going to use a so-called concurrent collector. And then we're also going to do in parallel and sequential. So if you recall collectors in parallel streams and streams, you have concurrent collectors which are designed to work when you have parallel streams. No point in using a concurrent collector for sequential streams. But you also have these things called non-concurrent collectors. And non-concurrent collectors will work both for sequential and parallel streams. So the question is, what are the performance trade-offs between these different approaches? And so as with the previous example for the joining tests, we're going to use the version of all this that has an array list, because we already know that splits and joins nicely. So let's go ahead and run the test, and then we'll take a look at the code and see what it does, and you'll understand why the results are the way they are. So here we're going to go ahead and crank away for the different sizes, and what you're seeing here is really quite interesting. So again, when we have a small number of elements, just 1,000 words, everybody performs about the same. When we go up to 10,000 words, you'll see that the sequential versions are, again, a little faster than the parallel versions because there isn't a lot of input. And there isn't much difference here. In fact, what you can also see is the parallel concurrent version is the slowest when we have a relatively small number of elements, n, which is just 10,000. But now, as the number of elements get bigger, now we start to really see things turn around. So what we're seeing here is that with large number of elements, parallel starts to win. And for the 100,000 word mark, which is about an eighth or so of the words of Shakespeare, the non-concurrent collector's winning, with the concurrent collector not too far behind. But once we get up to all the words of Shakespeare, now the concurrent collector is definitely winning by quite a margin, in fact, and the sequential versions are getting destroyed, and the non-concurrent collector is doing better than the sequential collector, but not as well as the concurrent collector. So those are kind of interesting results because they're showing you the diversity of the results. So let's go ahead and take a look at the actual code now that you know how things behave. Let's take a look first at collect to set. So collect to set is going to take this array list of words, and what it's going to do is it's going to go through in parallel, split things up using a splitterator, and it'll either have sequential or parallel streams going on here. Down here we do a little magic to just lowercase everything just to do some work, and then we collect everything together into a hash set. So what you're actually getting here is the number of unique words in Shakespeare. So we're collecting all the words in Shakespeare after lowercasing them, and we're going to end up with the unique words in Shakespeare. And this is a non-concurrent collector. So to collection will create a non-concurrent collector. And if you take a look, you see it, we're passing in the constructor reference for hash set. And as we saw when we looked at the results, the non-concurrent collector worked reasonably well, actually worked quite well for a moderate size number of words for the parallel version. But as we got larger number of elements, it got worse. So let's now go ahead and take a look at the other implementation. And this is the collect to concurrent set implementation. So collect to concurrent set is going to use a concurrent collector. So the non-concurrent collector, if you take a look at the non-concurrent collector, that's just what comes out of the box with streams, with the to collection factor method that makes a collector when you give it a type of map in this case, or a set in this case. There is no built-in concurrent collector for a hash set because there is no hash set. So I wrote a hash set, and I also wrote a concurrent collector for it. So let's go ahead and take a look at that. If we go over here and we take a look at the concurrent collector, this is a concurrent collector that collects things with hash sets. And I probably could have generalized it a little bit so you could pass in the type of set, but let's keep it simple for the time being. So here's what the concurrent collector looks like. We have a supplier that makes a new concurrent hash set, which serves the role as the mutable result container in Streams collector lingo. We have an accumulator that just returns the add method on concurrent hash set. We'll take a quick look at concurrent hash set in a minute. The combiner is a no-op because combiners are never used when you have concurrent collectors because everything collects straight into the underlying mutable result container. And then the finisher is also a no-op because when we're done, we have a hash set, concurrent hash set that's got all the values in it. And we set some flags. This is going to be concurrent. It's going to be unordered. And we have identity finish, meaning that we don't have to do anything else when it's done. So that's the concurrent hash set collector. You can see it's really quite simple. Here's the concurrent hash set itself. This is just a very simple wrapper around concurrent hash map. And I only implemented enough methods in here to do what I wanted it to do. So if you were going to implement, a true industrial strength concurrent hash set, you'd probably want to fill out more methods, but this is just what I wanted to do for my purposes in this example. So you are always welcome to extend it if you'd like to. So the difference, of course, between the concurrent hash set or a concurrent collector and a non-concurrent collector is the fact that the concurrent collector is going to not do the merging of intermediate subresults. It just goes ahead and stores the values directly in the mutable result container. So it uses the accumulator method to put it directly there. And that, of course, implies that you have to have proper synchronization for those methods. Otherwise, things won't work. Okay, so that was what I wanted to show you for this example. It's a cool example. It demonstrates how mechanisms like the choice of collection make a difference. It demonstrates how parallel versus non-parallel mechanisms scale up and show you different alternatives as well. So at this point, let me take some questions. And we will see what people's questions are. In the n times q model, q should have only non-blocking operations. No, there's nothing about that, I don't think. The n times q model is just trying to give you a feeling for when it makes sense to use a parallel stream. Let me go ahead and put my, there we go. So the n times q model is just trying to help you decide when to use a parallel stream. If n times q is large, and Brian Getz says larger than 10,000 or something like that, then use a parallel stream. You should probably play around with yourself to figure out what n times q should be for your machine, because obviously different computers have different speed processors, different amounts of memory, different amounts of core, and so on. So the queue doesn't really matter. If the queue is going to take a long time, then as long as you're careful and you use mechanisms like the common fork join pool managed interface mechanism, you shouldn't have to worry about that. How are ordering semantics maintained in the case of parallel streams? So as you probably recall, if you've watched some of my videos on this topic, the order in which the operations are run in a parallel stream is undefined. However, the order the results are produced is something that can be controlled by the programmer. And it's controlled basically by defining the collector semantics. So, and also, of course, it has to do with whether the collections you're working on have so-called encounter order semantics set or not. So things like lists have encounter order semantics set. Things like sets do not have encounter order semantics defined, or let me rephrase that. Hash maps and hash sets don't have encounter order semantics defined. So it all depends on the encounter order semantics and then the operations that you use. There's some really nice videos that I talk about this in detail, but the long and the short of it is that depending on the data types you're working on, that will help to determine the order in which things are done. And obviously the operations you use also determine that. So for example, if you sort something by using the sorted method in a stream, then obviously the ordering will have to be preserved for that, depending on the things you do, of course. You can also take advantage of different types of terminal operations. So for example, for each ordered will ensure the encounter order, whereas for each will not. But you have little or no control over the order in which the operation is actually run. And it doesn't matter. That's the whole point. You're not supposed to know. You're not supposed to care. Concurrent collectors will not have the merge step, and the accumulator is shared across threads. Yes, that's correct. It's called the combine step, but same idea. So concurrent collectors skip combining or merging, and they go straight to the underlying mutable result container via the accumulator, the method returned by the accumulator factory method. Where's the join API in the case of collector collect API? So the join API is taking place way down in the bowels of the Java Streams framework. You never see that as a developer of custom collectors. That's all done for you behind the scenes by the framework itself. So you don't know, you don't care. All you know is that depending on whether you have a concurrent collector or a non-concurrent collector, the right thing will happen, and the Streams framework, of course, is responsible for taking care of that. If they're blocking operations, there will be locking overhead. Not sure what you mean by that. If the operations block, there may or may not be locks involved, at least locks that you don't even see. There may be locks you don't see. For example, if you're doing I/O operations, then there may not be any lock operations that are visible to you. There could be lock operations deep in the bowels of the operating system of the virtual machine, but there's no guarantee that they're there, number one, and you have no control over them anyway. The main thread is part of parallel streams, and no thread sleep is needed in order to wait for parallel stream. That is correct. Why do we need thread sleep in the case of completable futures? Well, if you use completable futures correctly, you don't need to have sleep in the case of completable futures. If you use completable futures correctly, then you probably either have a server-side processing logic where you just let the thing complete and send its result back through whatever mechanism is used, be it a web call or a socket or whatnot. If you have a client, pure client-side completable future, then if you want to make sure you get a result, you would never sleep, but you would join. So joining on a completable future is actually quite equivalent to calling block on a mono in Project Reactor, or I think it's called get blocking or something like that, or blocking get with RxJava. So bottom line is there is never a good reason to use sleep operations with completable futures. If you're finding yourself tempted to use sleep operations, it's probably an indication that something's gone wrong in your program design and implementation. Let's see. So in the case of completable future, the main thread is part of the pool. So I asked this question. I don't really know what you mean by in the case of completable future, the main thread is part of the pool. Their main thread will not be part of the pool in the case of completable future, unless, of course, you call the join operation, which might go ahead and have the main thread pitch in, assuming that you call join in the main thread. But parallel streams and completable futures behave quite differently in that respect. Do I plan to cover concurrent collections in depth? Great question. Let me do something that will help to clarify that. Let's go ahead and go over here, and I will share my screen. So if you go to this link, you go to my Vanderbilt website, and you go to my digital learning folder or link, which you can also get to from my Modern Java by Example link, which says a link to somewhere. Let's see if I say where it is. Yeah, there you go. So no matter which link you go to, you can edit my digital learning stuff. If you go here, you'll find literally hundreds of hours of videos on all the topics that I go over briefly in these Modern Java by Example videos. So if you want to learn everything you could possibly imagine you need to know about concurrent collectors, click on my Parallel Functional Programming with Java and Android course and go down here a bit. And here we go. So if you go into some, I think this is like weeks 8 and 9, especially week 9. Week 9 walks through the internals of concurrent and non-concurrent collectors, shows you what they're doing under the hood, shows you how to implement concurrent and non-concurrent collectors, does some other comparisons, So there's tons and tons and tons of stuff. So I recommend you poke around here, and you'll learn everything you possibly could want to know about these topics. So I'm not actually repeating myself in the Modern Java by Example series. I'm focusing primarily on showing examples, but there's always stuff you can go back and look at for more information.